current. What is a catalytic current? What happens is when you make a catalytic current, you make this negative current on the outside of the cell membrane. So here you have your electrodes over here, and you're able to build up a negative charge on the outside of the membrane. Now, if you have negative charge accumulating in one part of the membrane, on the other side of the membrane, and guess what it's going to attract? It's going to attract positively charged ions around this area. So you get an accumulation of sodium, potassium, and other positively charged ions over here. So like magnesium, maybe a little calcium. There's a very small amount of calcium over there. So these positive ions start to accumulate because there is a buildup of negative charge on the other side. And this is going to accumulate around, what do we have here? Sodium channels. Now the positivity is going to cause this causes depolarization of the membrane. So the catalytic current, which is negative current, is going to build up positive charge. And this positive charge is going to cause the sodium channels to open up. So remember the little gates over here that we had? We had the M gate that was closed and the H gate that was open. Well, it's ready to fire now. This is the cocked state, and now it's going to open the M gate, and it's going to and the H gate is gonna start closing in a little while. It's a little slow. Think of a rubber band holding these two together. I mean, it's just an imaginary way of thinking of this. So in that time, you get your sodium gushing into the cell. Now this sodium that gushes into the cell is going to spread around and make the surrounding area more positive. And as it spreads all over in all directions over here. Now as it spreads, there are other sodium channels along the path that it will meet. So the sodium will, when you open the channel, the sodium that comes in, it gushes and it spreads around 2 millimeters in all directions around it. So it's got like a radius of spread of 2 millimeters. And this radius of spread of 2 millimeters will open other sodium channels in that area. And that allows more sodium channels to open up, and they will again cause more sodium to come in. They will spread, and this 2 millimeter area of spread is called current sink. So it spreads and spreads, and the current sink, it just sinks that current into the cell. That's how you should think about it, opening more of these sodium channels, causing a depolarization. And as you open these sodium channels, don't forget that there are potassium channels that do respond to this positivity, and it's going to cause the opening of potassium channels also. And potassium, if we remember, is more on the inside than the outside, so potassium tends to leave the cell, making it negative after some time. So this is a very brief introduction of how action potential works. Let's go through the phases of action potential now. So we have a situation where I'm drawing another axon over here for your benefit, okay? And here we have the different stages. So this is the current over here, the stimulator, and here you have your recording electrode. Recording electrode, one is inside and the other is outside the cell. This is stuck to the cathode ray oscilloscope. It's a voltmeter. The voltmeter is doing the recording, and the stimulator stimulating using catalytic current. Because catalytic current makes a negative charge build up over here, it is going to cause the cell to become positive on the inside. Now a catalytic is a negative current. And electric currents would actually cause a repolarization, or making the cell more negative over here. So we're not using that, and we're not talking about that right now. Now let's see what are the changes that the cathode ray oscilloscope stuck to the voltmeter would measure. We draw a graph, representing the different phases over here. And let's just say that the cell is in a resting membrane potential of minus 70 millivolts. It's around minus 70 millivolts. So it's minding its business. You suddenly decide to stimulate the electrode, and if you give a strong enough stimulus of around plus 8 to plus 15 millivolts, then this would cause this opening of enough sodium channels to reach a firing level. Oh, before that, let me just tell you what happens. I forgot one little thing. So we have the RMP, resting membrane potential. You build up this current, and this is your neuron, and it's floating in that water bath with all the electrolytes and the glucose and the energy and the oxygen that is required to sustain that cell. Now when you give an electricity, some of this current is going to spread in the water, because it's a salt solution. It's a brine over there. So the salt solutions conduct electricity very well compared to pure water, of course. And this is going to cause the current to leak through the water and reach the voltmeter. So it will cause a disturbance in the voltmeter in the beginning, and this is called stimulus artifact. What do we call this? Stimulus artifact. A stimulus artifact is just because there is a disturbance in the current, because it leaked through the water. It just flowed through the water and reached the voltmeter over there. So from RMP of minus 70, we had the stimulus artifact. Now things are happening in the axon along this path. You are going to develop an impulse, an action potential. It's going to spread, but it's going to take time for you to see these changes, because there's a distance that exists between the stimulator and the voltmeter, and so there will be a little delay and before you see any electrical activity. Now we call this latent period. Now the latent period is directly proportional. The duration of latent period is going to be directly proportional to the distance between the stimulating electrode and the recording electrode. So you make these things come closer, and the latent period won't be so long. And you make them far apart, like if the axon was quite long, then you will definitely see a increase in the duration of the latent period. Now eventually what happens is you will see a slight depolarization, and this is going to be in the shape of a hyperbole. Okay, so in your conical sections in mathematics you studied about this, and this is just a relatively gradual depolarization compared to what's going to happen next. So if you give plus 8 to plus 15 millivolts of current, usually that's enough to depolarize the cell enough to reach something called firing level or threshold potential. And what is firing level? Well, when you make the cell positive enough, you've opened up enough sodium channels to sort of reach something of a critical mass to allow self-propagation of this signal. You've opened enough sodium channels, so enough sodium comes in, spreads, and opens more channels and opens more channels. So you make this domino type of a chain reaction. And this kind of a chain reaction is helped by the fact that you opened enough number of sodium channels. And that is because you've given a strong enough stimulus. So this stimulus I gave caused a small change in current, and it's not yet action potential, but when I reach firing level, there is a very high chance that I am going to get a marked increase in the positivity inside the cell, because I've opened in a lot of sodium channels, and I suddenly get this very explosive current voltage change that takes place. And this rapid depolarization, because of opening of many sodium channels, is my action potential beginning, and this is depolarization. depolarization. And here the depolarization, it just goes all the way up to almost plus 35 millivolts. So it does cross 0 millivolts easily, and it just spikes all the way over there. That's why sometimes people call this spike potential. It just goes up like a sharp spike over there. So this is how your depolarization takes place. And why is depolarization happening? Because of the opening of sodium channels. So it crosses 0 millivolts in this giant squid axon, and this part which crosses 0 millivolts, we call this overshoot. Crosses 0 millivolts, it goes up to plus 35. Theoretically it can go up to plus 61 in the human being. And can you guess why? Because the equilibrium potential of sodium is plus 61, provided we have the same concentration of sodium of 140 on the outside of the cell and 14 inside the cell. You can watch the video on equilibrium potentials for further explanation. You can go back to that video. So that's depolarization. And what happens is after a millisecond or so, it just stops. Why? Because remember, sodium channels have two gates and they will close within a couple of milliseconds. So that's time dependent closure of sodium channel. Don't forget the word time dependent closure of sodium channel. So you get this little depolarization. Now what happens is you get to open the potassium channels. They start to open up. These potassium channels technically are supposed to open up at 0 millivolts, and they do eventually. And what happens is potassium channels open up and potassium starts to leave the cell. So you could see that the potassium channels open up, causing repolarization over here, and they're not as steep. The repolarization is not as steep as the depolarization. So we are making the cell more negative again on the inside, and that's fine, that's normal. And there's a slight slowing down again of the repolarization, and guess what's going to happen? Remember I told you that the potassium channels were sluggish. Why do you say that? Well, because technically if the potassium channels just closed here when we reached the RMP, that should have been enough, and that would have been well and good. But potassium channels are like bus drivers with hypothyroidism. They're quite sluggish. They're supposed to press on the brakes just before reaching the bus stop, but for some reason they press on the brakes after they reach the bus stop. So they overshoot. They go beyond the bus stop where they should have stopped, meaning RMP, and then they still cause a little more of a negativity to develop in the cell, and this further negativity is called hyperpolarization. Hyperpolarization, and that is going to cause a little more negativity to develop. However, hyperpolarization will never cross minus 94 millivolts. And why is that the case? Because minus 94 millivolts is the equilibrium potential for potassium. Alright, so the equilibrium potential for potassium, or the Nernst potential for potassium, comes to around minus 94 millivolts. You can't go more negative than that. The equilibrium potential for sodium is the ceiling for the action potential, and equilibrium potential for potassium is the basement, and you cannot change the voltage beyond these limits over here. Anyway, so the cell does get a little more negative, but eventually it does go back to its RMP thanks to the effect of the sodium potassium ATPase pump and the leaky potassium channels. You can check the video on RMP also for further details. The point is, this is your action potential, and these are the stages over here. Let's just go over it in a simple quick summary. So the action potential definition is, it is a series of rapidly occurring electrochemical events, that is to say depolarization followed by repolarization at the membrane of excitable tissues, when once initiated is propagated along the entirety of that membrane in undiminished amplitude, that is to say all or none law. So what happens is, we have this kind of a setup with the axon, and you've got the sodium channels and potassium channels, and the sodium channels are they have two gates. One is a H gate and an M gate. The M gate is on the outside facing the ECF, the H gate is on the inside. Potassium channels only have one gate, they're quite simple. And Hodgkin and Huxley studied the action potential in the giant squid or the loligo. Now, action potentials happen in only certain tissues like neurons, skeletal muscle, cardiac muscle, pacemaker cells, and smooth muscles. Which kind of smooth muscles? Single unit or unitary smooth muscles, not just every type of smooth muscles. Now, what happens is, the action potential builds up. How this is an impulse, and it carries the signal across a long distance. So to study the action potential, we have this kind of a setup where we have stimulator and we have a recording voltmeter, a recording apparatus, which is a voltmeter. This voltmeter is attached to cathode ray oscilloscope. The stimulator gives a current. Which kind of current? Catalectric current. And all these electrical changes are picked up by the voltmeter on the other side. So remember the sodium channels. Here's the little diagram that helps you remember and recap all of this. And how it works is, the M gate swings open when you make the cell a little depolarized, and eventually the M gate will open and the H gate will close. So from a resting, cocked, or ready state, it then becomes inactive, and the only way to make it active is is to repolarize the cell. That is to say, to make the cell more negative. Potassium channels have a single gate, and when they open up, they become they cause the efflux of potassium from the cell, and they're quite sluggish because they cause hyperpolarization. And so what happens is, the catalectric current that is given over here on the axon is going to cause negative charge to build up on the outside of the neuron, and this negativity that is built up on the outside of the neuron will attract positive ions on the inside of the cell, on the inner surface of the neuron. This positivity will cause the opening of voltage gated sodium channels. And if the catalectric current is strong enough, how strong? Around +8 to +15 millivolts, then what are we going to get? We are going to get to reach firing level. Firing level is where, if you reach firing level or threshold potential, you are very likely to get an action potential. If you read the books, certain books, it would actually say that threshold potential or firing level is where you have a 50% chance of getting action potential. Books like Byrne and Levi give such a name, such a term. But most other books would say that it is where you will definitely get an action potential. Just be aware of this. So you have the depolarization taking place, and this depolarization is your what do we say? It happens after the latent period, and it is hyperbolic in shape, and it isn't an action potential immediately. This is your local response. What do we call this? Local response. It's a small current. Now, if this current has crossed +8 to +15, so let's say -55 millivolts, then we are going to get a spike potential where we will get rapid depolarization. So sodium channels are going to cause spread into the cell and cause opening of more sodium channels and more sodium channels and more sodium channels. We call this kind of a positive feedback system the Hodgkin cycle. Hodgkin cycle, where lots of sodium comes in, causing more channels to open, more channels to open. This is an example of positive feedback. Positive feedback. Alright, so because more sodium comes in, spreading around, in its current sink, opening more sodium channels and opening more sodium channels. It'll reach up to plus 35 millivolts in the giant squid axon. It does not mean that your human neurons are going to always reach plus 35 millivolts. Human neurons are smaller in diameter, and they usually reach around 0 millivolts. They do not depolarize to plus 35, except for some of the large neurons in your sciatic nerve or peroneal nerve. You are unlikely to get an overshoot in the depolarization above 0 millivolts. Just be aware of this also. So you cause this one, time dependent closure of the sodium channels. They close in another in a millisecond or so, and after that potassium channels open up. Actually, potassium channels open up at 0 millivolts because, like I said, in the human being we don't reach plus 35. 0 millivolts is enough to start opening the potassium channels. So then you get this repolarization taking place. The cell repolarizes and repolarizes, and the conductivity to potassium is increasing, and eventually it does decrease. So again, it's a little slower, and as you could see, the potassium channels will hyperpolarize and go deeper, much lower than RMP, but they can never go lower than minus 94 millivolts because that is the equilibrium potential of potassium, or the Nernst potential of potassium. Eventually RMP is restored, and that is your action potential in a nutshell. You can draw this diagram of the graph, and right under it you can also correlate the different phases of conductivity of sodium over here. So I'll just draw one more little thing. So here is your RMP, stimulus artifact, local response, and from local response we are going to get spike potential, depolarization, overshoot, and repolarization, hyperpolarization, and back to normal. Now this, we know these phases. Now look at this, sodium channels, however, let's draw sodium conductivity in red, and let's see how the depolarization and sodium channels correlates. We get this massive increase in sodium conductivity. Okay, usually it is given in the terms G. G refers to conductivity, G and A, conductivity of the membrane to sodium. Potassium channels, they will start to open up at 0, so potassium is almost 0, and then somewhere over here the potassium conductivity increases and then it decreases. This is GK. If you can just draw this in the diagrams also, and put this in your mind and even commit it to paper, I'm sure it would help you get even more marks.